So the
Most of the
light
light that
will,
we can see that we use for image formation, when it hits our body, it gets absorbed by stuff of the body, but
yeah, yeah,
not so much for the longer wavelength light like near infrared.
absolutely. And what happens if an infrared photon, say at 800 nanometers, an infrared photon hits my skin?
Mm-hmm.
It'll penetrate probably a couple of millimeters at 800, maybe even more at 800 nanometers. It'll propagate untouched to a millimeter or so, and then it'll hit something, which will be a cell wall, say, and it'll scatter. And since there are no pigments around, it won't get absorbed because there's nothing to absorb it. So it'll scatter. And some of the light will scatter straight out again, some of the light will scatter deeper, some of it will scatter sideways, and it'll perform a random walk through the body.
Mm-hmm.
And this is what happens to the infrared photons. They bounce around many times inside your body
Mm-hmm. They kind
until
of get
they get
stuck in your
to
body. They're pinging around.
they're pinging around until they get absorbed by something, and the absorbers are very rare. And
Mm-hmm.
if have you seen the famous picture of my hand
Yes, yes,
with the
yes,
veins?
yes.
Deoxygenated hemoglobin has a significant absorption in the near infrared, and that's
Mm.
why my veins look dark.
Yeah, yeah,
It's
yeah,
projected against the diffuse
yeah.
light
That's what, yeah,
coming
if you
through my
go,
hand.
anyone who has a red light at home, you often, if you look at a mirror, you can kind of see all of your vasculature very clearly.
Yeah, yeah, exactly. And in fact, if you get a lamp and you put your finger over a flashlight, you'll see red light coming through.
Yep, yep,
And you think,
yep.
oh, that's due to hemoglobin. No, it's not. It's due to the sunset. It's scattering. And you
Okay.
scatter the
Yeah.
short wavelengths first and the long
Yeah.
wavelengths
So there's a
last.
lot of this near infrared light coming out of the sun. Life,
Yeah,
in some sense, seems to be tuned to it. And when that light hits our bodies, it pings around inside of our body for quite a
yeah,
while, but
yeah,
eventually it will run into something that can absorb and
yeah,
interact with it.
yeah, yeah. And that's the point. But that's the first order answer to this question. It actually gets more complex and more interesting than that. We can follow this scattering. I mean, I can do it here with my spectrometer. I can shine light into my hand and I can look at light coming through the other side. And I can measure the distance the light's traveled by measuring the water absorption in the light that comes out. Because half our body is water.
Mm-hmm.
And if this light scatters many times, it takes a longer path through my body than just going straight through. And it could be much longer, a factor of 5, 6, 7 times longer. And it will suffer all the way. It will suffer from water absorption. So if I measure the water absorption coming out of the top of my hand, I can say how far it's traveled through water.
Yeah.
It's quite a long distance that it travels through water. So that's one experiment you can do. It's actually a flawed experiment, but the idea is there anyway. So what happens? And this is very important. This is do you know about IKEA stores, furniture stores? Do you have them in the
Yes,
US?
yes, IKEA.
Yeah, you know all about IKEA. When you walk into an IKEA store, they take you all the way around the store in this zigzag path, don't they?
Yes,
For
yes.
miles before you get out. That's what the photons do in your body. They
Mm-hmm.
scatter many times. Like a pinball machine, you scatter into a pinball machine
Yeah.
and you get bounced around by lots of pins, which don't give you any prizes. And eventually you might win a prize.
Mm-hmm.
It's like an airport departure lounge.
Mm-hmm.
They
Mm-hmm.
take you through all the duty-free places
Right, right,
through
right.
this zigzag path
Yeah.
before you get into the lounge.
So this
So
light is
it's a
kind of
very,
going everywhere in the body.
yeah, it's going everywhere. And of course, taking a long time to do that. So if you get, so many photons per unit volume hitting your hand, it's like cars going down a freeway.
Mm-hmm.
I'll try and speak American. It's like cars going down a freeway. They're all driving at, say, 50, 60 miles an hour, whatever they do. And, you get a lane closure and suddenly you get a blockage and they're all going at 1 mile an hour and they're 2 meters apart instead of 100 meters apart. So what happens when these photons go into your body? They scatter many times and the photon density builds up because they keep coming.
Mm-hmm.
They're not being absorbed very quickly. And so it's like pumping up a balloon with a small hole. you pop the balloon with photons, and you get, you increase the pressure in the balloon, and you get lots and lots
You're
of photons in
accumulating
the balloon.
near
So
infrared light.
you've got a very high photon density in your body, which is looking for somewhere to be absorbed. Some of those photons will escape the other side, and we see that in the paper that you wanted to talk about. We can shine light right through the chest from front to back. So some of the photons will get absorbed, but there'll be a lot of photons in there. So you've got quite a high photon density inside the body, more than the outside. It's a bit like shining light through a high refractive index window.
Mm-hmm.
The light will slow down because of the high refractive index. And so in that distance, you'll get more photons than you would without the glass there. So, it's not anti-physical, it's a simple physical phenomenon.
Mm-hmm.